Okay. So we were talking about IMS, Intermolecular Forces, right? And you guys are very familiar with all of them. We had dispersion forces, we had dipole, and we have, you remember all of this, right? Yes, no, maybe?
Yeah.
Most of them.
Okay, good. Okay, so now if we take a look at some of these dispersion forces. So if we know, like, for instance, fluorine, my table's all screwed up, spelled. Fluorine is a diatomic. And but if we go down the halogen row, right? We have fluorine, we have chlorine, we have bromine, we have iodine, we have astatine. Now, as we get bigger in size for each of those, and we also know that the size also gets larger as well too, the atomic radius. Are you with me so far? Right? And so if we pay attention to that, we also notice that the melting points actually go up as well. And then also the boiling points for these guys go up as well. And we kind of talked about that a little bit on Thursday. I think that's where we kind of left off. Is that correct? I mean, on Monday, sorry.
Yeah. Yeah.
Okay, good. Okay, now the reason why this is the case is because as we get bigger, that radius also gets bigger. That also means that the electrons that are building, those shells are also getting bigger. So you have more access to those shells compared to the nucleus. So the distance between the nucleus and the electrons, the valence electrons, are even further apart. And so that means that you also have those electrons there to sit there and involved in like your dispersion forces or your polarization ability as well. And so you're able to induce those guys better because they're bigger in size. And so because of that, you'll notice that they're going to be a little harder to disrupt, to break up in terms of the molecules. So they're going to take more energy to sit there and separate them because you have more forces that are able to act on that. Does that make sense? Yes, no, maybe? So let me see if I can say this a different way. I know we just jumped in. So this is going to represent the nucleus, right? So in terms of fluorine is really close to the nucleus. The electrons are sitting around here, around it, right? This here is going to represent the nucleus of chlorine. Well, chlorine, you have a whole nother layer, right, of electrons to sit there and play around with. And then bromine, here's your nucleus, right? And then you have, I should just draw these in a circle. We have okay, so you have a further distance for these electrons. And so these electrons will be more accessible for inducing, for interacting with, because those valence electrons, because it is further away from the nucleus. The nucleus is not pulling them so close together. And so in that context, you're able to sit there and get more dispersionary forces to sit there to occur between all of those electrons that are existing between here and the nucleus compared to what you have in the case of fluorine, right? And so in the case of your dipole, since they're interacting, your diatomic molecules, these guys are going to be interacting. And so those electrons that are going to be surrounding it, right, they're going to be able to be induced. So even if it's polar or if it's non-polar, you're still able to get dispersionary forces. And then also, since you have more layers of electrons around it, those electrons are going to be more apt to be induced by other things as well too. Does that make sense? By other molecules.
So like the further away from the electrons are from the nucleus, the more likely they'll be able to get induced
That
through
is correct.
dispersion forces.
They can actually get more interactions occurring because you have more electrons there to interact with. Does that make sense?
Yeah. Okay.
Okay. And so, because if you think about it, it still boils down to that, like you're inducing those charges, right? You're messing with those electrons. You're attracting it by pluses, or and so it allows it to sit there and be swayed. And so you have more and more of them to interact with in that case. And so as we get larger in terms of the radius, that means that we're going to be able to sit there and make more charges, more stronger dispersionary forces in the case when the molecule is heavier or bigger than in the case of when it's a smaller molecule. Okay, so clear that. Okay, so let's say we have something that weighs exactly the same. Let's say we're looking at isomers of pentanol or pentane. Pentane is C5H12. Okay, so if pentane is C5, then H12, and there's 3 different forms of pentane. We have what we call, show you. We have neopentane, where we have a carbon in the center. We have the 5 carbons here. The 4 carbons surrounding that center carbon. We have isopentane, where we have, again, a center carbon, and we have 3 of the carbons surrounding it, and then the other attached to an H. And then we just have a carbon on the other chain. And then we have N-pentane, where it's just chains of carbons that are connected. Okay? So if we look at this and we look at the the boiling points of these guys, right? They're different. Neopentane is a 9.5 degrees Celsius. The isopentane is 27. And then the N-pentane is 36. So why do you think there is a difference, even though they all have the same chemical formula, C5H12? Anybody want to take a guess? So in this case, the molecular weight is all the same, right? What is the distinction between 3 of the molecules, all 3 of the molecules? Ooh, somebody said something, hold on. Okay, I like that. Mauricio says, it says contact. So the contact area. So if we take a look at this, right, we have this carbon basically shielded by all the other carbons on the outside. So it has less contact area than this carbon. Than this hydrocarbon here, right? The isopentane. So in this case, we have 3 of the carbons kind of shielding that center carbon, but we still kind of have a little more room with just that hydrogen there, right? Because if we think about this, right, the structure, let me draw it out in a little more detail. So here you have that carbon. This represents that carbon with H, H, H. And then that's connected to that center carbon in the middle. Okay. And then, so you can kind of see it in the figure. This guy is kind of lumped in. Your center carbon has less ability to interact with anything other than the carbons that are surrounding it. So no other molecule could kind of get in there and to interact. So it has less surface contact than this guy does. So this guy has more surface contact than this guy. Okay. And then as we linearize this, right? And so you just have a long chain of carbons surrounded by those hydrogens. You have more areas to contact. Okay, so if you have molecules of the same thing, they're going to be able to interact more with the one that has more area to contact with compared to the one that has less area to contact with. Does that make sense? Okay, so let's look at it like this. Okay, you're doing laundry, right? Have you guys done laundry before?
Yeah.
Oh, yes.
Okay, so only two of you guys, so I know the rest of you guys are stinky. Is that what you're telling me? So I heard only Mauricio and Gracia do laundry. So I know not to stand to next any of the rest of you. You guys don't do laundry. Is that right, Alex?
No,
I
I do
think
laundry.
You
Like
say you
six,
do?
7 people live in my home.
What was it? You say you don't do laundry?
No, my internet sucks right now.
Okay. Yes, do you do laundry? I guess she's not there either.
I'm here. I'm here.
Oh, you're there? You do laundry? Okay.
Yeah, I actually, yeah, I have to do my family's laundry. So yes, I do.
Okay, so let's say we have let's say a person in our family had a little bit of an accident. Like we'll say it's a baby or a kid or something like that, and they kind of pooped, right? And let's say we crumpled it up around, they pooped in their undies or their pants, okay? And we crumpled it up, right? Just kind of tied it up real tight, okay? So, and we throw that in the laundry. Now compared to somebody who pooped and then we kind of spread it out a little bit more, right? And then somebody who pooped and spread it out, like completely laid it out completely, and we threw it in the washer, okay? Which one is going to get cleaner? The one that's crumpled up or the one that's going to be spread out just a little bit, or the one that's spread out completely?
Spread out completely.
Why?
Because it's easier to access when clean.
That's right. Okay, so this is the same concept. If you're spread out, the further you're spread out, the more area that you have contact to, you have access, right? You have more access points. So you can make more and more dispersionary forces, right? If you're clumped up, you're going to have less points of access. So this guy here is all clumped up, where this guy is all spread out. Does that make sense?
Yes.
Okay, so because of that, you're going to have more and more interactions. And so those forces are going to be stronger because you have more points of contact compared to here, right? And since you have more points of contact, it's going to take more energy to disrupt that contact. So it takes more temperature to sit there and make it boil, right? 36 compared to 9, right? 36 degrees compared to 9 degrees. So you need to put less energy into disrupting this because they don't make real contacts because they're being shielded from that contact. Does that make sense?
Yes, it does.
Okay. Okay, so let's see your skills. Now that you have some insight here, where am I? Sorry, my computer is acting crazy today. Okay, so here's the question. It says, order the following compounds from group 14 elements and hydrogen from the lowest to the highest boiling point. So we have CH4, we have Si4, we have GEH4, and we have SN4. And then I want you guys to explain why, okay? I'm gonna put you guys in groups. I'm gonna give you guys about, say 5 minutes. Because this morning I gave them 10 minutes and like 3, So I figure you guys should be able to get it done in about 2, right? let's see, 2 groups of 2. Okay, rooms are open. Okay, you guys are back. So what did you guys think? Group 1, that is Alex, Angela, and Gracia. You guys tell me, write down your order. And group 2, that's Mauricio and Mikey. You guys write down your order. And then we'll have you guys explain. So one of you guys write on my board. Can you guys see my board?
Yes.
Yeah, I'm just looking for the annotate option. I cannot find it for some reason.
So
You
it'll
guys
be up
want me to
top.
write it down? My group?
Yeah, I've done it like multiple times before. It's not there. Oh, you know what? I just had to full screen it. I figured it out. I got it.
Okay.
From highest boiling point?
From the lowest to the highest.
Oh, well, oh.
Oh.
Can you read my handwriting?
Your handwriting is almost as good as mine. Okay. So you guys look like you agreed in terms of the order. So why?
Mhm.
It's
You
because
guys,
the smallest has the lowest boiling point that needs the least energy.
Okay, why?
Oh.
It
okay,
has the
so
least
like,
contact, like least surface area.
Okay.
so those, so they are non-polar, so they may like experience a little bit of dispersion forces. So let's say like if we have smaller, like if it's the molecule smaller, so
Uh-huh.
the less polarity it would have because it's weaker. So the dispersion forces, they're like that. It's like that for that part. But when it comes to a larger molecule, then I guess the larger the dispersion would be.
Okay. So Mauricio says, he says that they have pretty much the same contact area, but since the atoms are bigger, they're going to have a stronger dispersionary forces. So they're going to have more access to those electrons to sit there and kind of be induced and be. Is that right? Is that what you're saying, Mauricio? Yeah. Okay. So yeah. So it's in this case it's based upon the size. So you guys are all kind of right, Because initially we have this little small atom, and when we're thinking about it, it's kind of like you have less access because you have less electrons to access. But we get more and more and more as it gets bigger. So that layers of electrons, you have more and more electrons that can be induced, so that they can actually cause more and more forces to occur, more dispersionary forces, and they'll be stronger because it's kind of an additive type of effect. The more you have, the stronger it's going to be, right? Does that make sense?
Yes.
Okay. Let's see. Okay, so this is just basically showing you a graph of the, as we increase in atomic size, these guys, the boiling temperature actually also increases. So it gets closer to 0 in this case. Okay, so in real life, this is occurring, right? So do you guys know a gecko or a lizard, right? So a gecko basically has seta, and they're just basically little tiny hairs. And these hairs, at the end of them, they have these little spatulas. And that spatulas, they get little stickiness to them. And all of that is a result of the dispersionary force. They kind of get induced. So the lizards sit there able to crawl up walls. Are you guys able to crawl up walls? Anybody Spider-Man out there? Yeah?
No.
I'm assuming yeah, because you guys aren't saying anything. So you guys, okay, so you guys can't crawl up walls like lizards, right? And
No, I'm not that sticky.
and so they're basically using those dispersionary forces to sit there and interact and causes them to adhere to that wall. And since you have a whole bunch of these little ones, it actually sit there and builds upon itself, giving it a little more stickiness, okay? Because it's covering more contact surface area. Okay, let's see. Okay, so we know that dipole-dipole attractions also play a huge part. Now, dipole-dipole is going to be stronger than dispersionary forces, and they're going to happen in the case of polar molecules. And so in that case, we always have a positive pole and a negative pole, and then that positive pole is going to be interacting with that negative pole. And so you're going to get that nice attraction occurring based upon that partial positive and that partial negative, okay? Now, when we talk about hydrogen bonding is just a special case of dipole-dipole. The only thing different about it is that you're working with the the elements that have the highest electronegativity. So that's your nitrogen, your oxygen, and your fluorine, okay? In it, that are gonna be covalently attached to hydrogen. So since they have a high electronegativity, it's gonna pull the electrons really close to themselves, and that hydrogen is gonna have that partial positive charge. And then in this case, the oxygen, it's gonna have a partial negative charge. Now, since these guys are so small and they have a strong electronegativity, they're going to have a strong type of interaction. So that interaction is going to be much stronger than what you see with just a regular dipole-dipole. Okay, so hydrogen bonding is going to be significantly stronger than the other. So now let's think about this, right? If we have H2O, we have H2S, we have H2Se, and we have H2Te. Or if we have HF, HCl, HBr, HI, and, or if we have ammonia, pH 3, AS, H3, and SB. Okay, so we have this group, this group. Oops. This group. Okay, so we have these three groups. So what I'd like you guys to do is give me the one who would have the highest melting temperature. The highest boiling points. And for all of these in their groups. Okay, so do the same thing that you just did, basically put them in order of their boiling points. Okay, and then be able to explain it, what you guys think is going to happen. I'm going to put you guys in some different groups and see if you guys can figure that out. Are you with me? Do you understand what I'm asking you?
Yeah, just let me take a picture of the question real quick.
Okay.
We put it into different, just put it into different groups.
So put them in the order from the lowest boiling point to the highest boiling point.
Okay, okay, for all of them?
For all of them. Yeah.
Okay.
Okay, you have some answers?
Dr. Henry, I just want to make sure the one at the very bottom right, that's SBH3, right?
That is correct.
Okay.
Okay. So let's see. Let me clear my screen. Okay, so group one, that's Alex's group. And group two, we'll put you guys over here. So give me your orders.
Quick question. Do we have lab after this?
Today you don't have lab, so you guys get
No?
another break. Yes.
Okay.
Yeah. But next week, you're going to have about 3 of them. So, but they're fun labs. The next ones are going to be fun. You get to use the rest of your glow sticks.
What do you mean?
What was that? What do I
What do you
mean?
mean 3 labs?
What was that?
Yeah. What do you mean 3 labs? We have lecture 2
labs.
days.
We only have 2 days. We only meet for 2 days.
Well, for the lectures next week.
Oh yeah. Oh, so I guess we'll have 2 labs. Darn it. I thought I was gonna get you guys talk you into another day because I know you guys love my class. So okay, so let's get those guys in order on the board so that we can move it along. Okay. So Jess, I sent an email just now and we'll see if they respond. Fix it.
Okay. Hopefully they do.
Yeah, it's a loop. I think that they have it set up in a loop. And so
Mhm.
it says you got to have the other one before you get this one. You got to have this one rather than, you know.
Right. Okay.
Okay, I see Mauricio's group. And then oops. Did you guys put your other one down or did I not see it? Michaela,
Yeah,
That's
sorry.
it.
I will write them right now.
You guys want to explain yours while they're writing theirs down?
Which group was that directed to?
That was correct, directed towards group 1.
All right. So basically, the same concept as the last example, since they basically all have the same contact area. We base it on the size of the atom or the radii.
Okay. Okay, but you
Sorry
wrote,
about that. So
what was that?
we were basing it on the size of the radii of the atom.
Uh-huh.
And since we're on hydrogen bonding, there was a twist. So the
Okay.
ones that are hydrogen bonding are the highest boiling point.
Okay. Okay, so that is correct. So Mauricio's, your group is actually correct. So we'll go over it real quick. Group 2, you guys are basing it solely on size. Is that correct? Mikey?
Yeah, sorry. I keep tabbing out and then I go to like hold the space bar to unmute and I'm not tabbed in. My bad.
Okay.
But yeah, that is all we did.
Okay. So, and you guys didn't take into consideration hydrogen bonding. So
Wait,
hydrogen bonding has a much stronger effect. And so, and
Dr. Henry.
yes,
I honestly, Mauricio, when you were explaining it, I had a hard time like hearing you through my speaker. So I just want to
Okay.
make sure that when we talked about it in the group, Mauricio, was it about the electronegativity? Is that what you said?
Yes.
Okay.
About that too, and the size of the.
Okay. I just wanted to make sure that that was right.
yes. Okay. So this is what we would expect. If you guys take a look, let me clear your answers there. So this is what the figure 10.11. So we have our H2S, H2SC, H2TE, right? And then if you looked at the trend and based upon what you guys had learned based upon size, we would assume that H2O would be lower than H2S. But in reality, H2O, we know from experience, is all the way up here, 100 degrees, okay? 100 degrees, water boils at 100 degrees Celsius. And that's because of the hydrogen bonds. The hydrogen bonds are very strong compared to the dipole-dipole interaction, okay? Because of the strength of those hydrogen bonds, it causes those guys to stick together better, okay? Does that make sense? No, yeah. Well, obviously group bonding does because that's what they got, right? And then that's the same thing here with hydrogen fluoride and ammonia, right? And so you see you have these they're up here, and then the rest of them are below that. And that's because these guys, they're gonna have dipole-dipole, right? But that dipole-dipole isn't as strong as the electronegativity effect that the oxygen has with the hydrogen, and the hydrogen has with the fluorine, and the hydrogen has with the nitrogen. Does that make sense? Are you with me?
With you?
Yeah.
Okay. Okay, piece of cake, right? So this is all going to be an exam, so I'm going to throw a lot of curveballs, since there are a lot of calculations with this. Now, we see these effects and how important they are in terms of nature as well, too. Your DNA molecules is made up of a double helix. Those double helix are interacting via hydrogen bonds. So those hydrogen bonds keeps our DNA intact together so that they don't become unwound, okay? And they help in terms of the primary structure, and then also a little bit with the secondary structure in terms of that twisting, because it's a helix, a double helix. Okay. So if we take a closer look at the DNA molecules, so we know if you guys took biology, A interacts with T and C interacts with G. Well, A stands for adenine. So the adenine has 2 points where it forms hydrogen bonds with the thymine. Okay, and you guys can kind of see the hydrogen bond forming between this amine group and this this double bonded oxygen at the end. Okay, on the nitrous ring structure. Okay, and then here you also have that nitrous group, that amine group on the nitrous structure, are forming with that amine group in the ring structure there as well too. Okay, and then in the case of G and C, guanine interacting with cytosine, you also again form hydrogen bonds. Okay, so it plays a real role, important role in basically our survival, keeping our DNA intact. Does that make sense? Do we have any mutants out there? Anybody with 3 arms or legs?
Maybe.
Maybe. Okay. Okay. Okay, so the IMFs are going to play a huge role in terms of the physical properties of liquids, and we've kind of been pushing it. You've kind of starting to see how they interact, and those the more IMFs, intermolecular forces, that you have, the stronger it's going to be. That means that those boiling points are going to get higher, right? And like in the case of water, compared to that of dihydrogen sulfide. Okay. They're also going to be important for cohesive forces. Cohesive forces are basically molecular interactions between identical molecules, and adhesive forces are molecular interactions between different molecules. Okay. How many of you guys have ever had to stick your hand and they use the capillary to get the blood to test your blood sugar? Any of you guys did that before?
Yeah.
All right. Okay. So why does the blood go into the capillary?
Is it because of the oxygen on the outside?
Nope, it's not because of the oxygen.
Hmm.
How many of you guys have spilled
Mercury,
wine
repeat the question.
and used a paper towel to pick it up? I said
Wait,
what?
Oh,
Oh, go ahead.
oh, they're bonded together, so they just like flow with each other, I guess.
Is it because they're bonded together? So is it actually a real covalent bond that's causing everything to flow together? So are you saying all your blood is all bonded together?
Intermolecular forces.
Yeah, that's right. It's those intermolecular forces, right? So in this context, and I'll show you a figure here in a second. Right? In the context, you have the adhesion factor, and you also have the cohesion factor. Cohesion, meaning molecules are the same. So in the case you have blood interacting with blood, right? So you have your blood interacting with blood, but the blood interacting with the glass has a stronger effect. It's greater. So you're getting suction, you're getting the blood running up the tube because of those factors, right? The blood says, oh, something new, let me, go up that. And so it's interacting with the glass tube that's being used to sit there and collect the blood sample. Does that make sense? So it is those factors that are going to be playing a part. And we're going to talk about that. You're going to see some images of that. I'll go over it a little bit more. Sorry, there we go. Okay, so one of the things I want to talk to you guys about is viscosity. Viscosity is the measurement of resistance of flow. Okay, so what causes something to become more viscous? If it's more viscous, that means it's more resistance to flow. It's not going to flow as well. So how many of you guys eat honey? You like honey in your tea? Honey in your whiskey?
Yes.
Okay.
Yeah.
So, and when you pour honey, does it just like run out like anything?
No.
No, it's a job, right? To sit there and get the honey out, especially out of the little
Mhm.
jars, the little bear jar, right? And you're trying to squeeze and squeeze to try to get as much honey out as you can. Or you
Yeah.
put it upside down, let it sit for hours and hope that you get some of it coming out. Or is that just me?
Yeah, that happens.
Okay.
No,
It
just
happens, right?
Sometimes I heat it up in water.
You heat it up in water. Okay. Okay, so we know that honey is very, very viscous, right? It's thick, it's sticky. So what can we assume about honey? What are some of the things that we can assume about honey? Since we know that it's very, very viscous.
Are the molecules closer together?
Is it that the molecules are closer together? Is it a solid?
No.
The molecule
The bond,
interaction is very stronger.
intermolecular.
Would it be liquid?
What was that?
Would
The
it be
bond.
liquid since it's kind of sticky and obviously the molecules are like going around at the same time?
So yeah, we know it's a liquid, right? Because it flows. That's
The
part of that
bond.
concept, right? But why
Mhm.
is it so sticky? Why is it so viscous? What makes it so viscous? Why is it so resistant to flow?
The bonding in them, right? Or
Yeah, I think they're
Forces?
like really so
Intermolecular.
attached to each other.
Okay, wait. Somebody said, I heard, sir, intermolecular forces, right? So we can
Yeah.
make an assumption that there's probably a shitload of intermolecular forces in honey. That's the reason why honey's so thick. But water, if I put there and I decide to pour water on my computer, right, it's just gonna flow out. But if I have, decide, or not on my computer, say on my girlfriend's computer, right? I get mad at my girlfriend, I'm gonna pour water on her computer, right? I'm not gonna pour honey on a computer because by the time I start to try to get the flow out, it's taking forever, right? It'll take another hour before it actually gets out there enough honey to sit there and cause any damage, right?
Yes.
And so she'd have plenty of time to come up and knock the honey out of my hand, right? But if I have water, it's gonna flow very well, right? Water
Yes.
has those forces, but those forces are not as great and as many as you would have in the case of honey. Does that make sense?
Mm-hmm. Yes.
Okay. What about motor oil? How many of you guys love motor oil? Tastes delicious, doesn't it?
Ew. I just put some in my
Yeah.
You just put some in your car. Did you get some on your hand? Are you
no.
good?
It's it kind of smooth a little bit, but I wouldn't say it's as thick as honey.
Yeah.
Yeah, it's really oily.
But it's
It's
still
really
really
oily.
it
But
comes
it's
out
a
of
little,
really oily.
yeah.
it's a little viscous, but it's nowhere near as viscous as honey. So if we do the comparison between honey, the viscosity of honey compared to the viscosity of motor oil, honey is about 2,000 to 10,000, right? And it's going to vary because we know that when we talk about honey, honey has all of these things. They have, those sugar chains that are going on there. It has some of those proteins and stuff like that. Because of all of those different interactions that are occurring, it causes it to be nice and sticky. Where in the case of motor oil, right, it also is viscous, but it's nowhere near as viscous as honey because it's more uniform, although it has some variability in it, but it's more uniform than it is. And then we also know that the majority of those are just dispersionary forces, right? Because it's a hydrocarbon.
Oh yeah, but it depends on what type of honey are we talking about, because we're talking about the honey that is actually organic, the ones that comes from the bee's nest, then that's really thick. Because I have like over here honey from El Salvador and it's really thick. It's so hard to get out.
But all honey is organic. All honey comes from bees. It just comes from different pollen, so, or different flowers. So I should say pollen. Okay.
Sometimes they have fake honey.
What was that?
Sometimes they have fake honey, like they dilute it with other things, but you can't really tell.
Yeah. So they'll put just glucose sugar in it and stuff like that, a syrup. So they'll heat up the sugar and mix it in. And it'll still behave very viscous because of those interactions, right? Because we have a lot of oxygens and hydrogens that are in there. And so they're going to be forming those polar bonds and stuff like that. And then you have those polar bonds that are going to be acting as dipoles for other molecules. And so you're going to have a lot of, stickiness going on.
Thickness.
Right. Okay.
Everybody trying to prove Dr. Henry wrong.
It's okay. I'm used to it. Okay. So cohesive versus adhesive. Cohesive means what again?
The same.
The same. Adhesive means different, right? So in the case of, we have a bug on water, right? So the bug's feet interacting with the water, right, causes it to have a little bit of a surface tension, okay, because it has those little hair-like follicles at the surface, and so it's able to sit there and float on water. Don't you guys wish you guys could just walk on water? She's saying.
I don't know how to swim, so I will just go down.
Okay, so because of the surface tension, right, it uses the fact that there's surface tension, and that is using, what forces do you think it's using? The bug sitting on top of the surface of water? Is that going to be adhesive forces, or is that going to be cohesive forces?
Adhesive?
That's right, it's going to be adhesive forces, okay? Where the water connecting to itself, holding itself kind of together, that's going to be cohesive, right? So the water molecules down here, okay? What about in the case of water collecting on a spider web?
Cohesive?
So,
Oh. Adhesive?
or both, right? Because first off, it's going to have to collect on the spider web. So that part is going to be adhesive, right? Two different molecules, spider web and the water. And so the water is going to start nucleating, getting bigger and bigger and bigger. So your drops get bigger. So that's going to be a cohesive component. And then what about, let's say, water versus mercury? So if you look at it, it's really hard to see. It's real tiny. But mercury forms a meniscus like this. And water forms a meniscus like this. Do you guys remember what a meniscus is?
Yeah.
Okay.
It's the center point.
Yeah. Okay. So why does mercury form an inverted meniscus where water forms that U meniscus? Which forces would be greater under which circumstances? Are you there? So we have cohesive forces or adhesive forces. Which one is going to be greater? And why do you think? In the case of mercury.
Cohesive forces.
Okay. So cohesive forces are going to be greater. And you can tell that that's the reason why you have that protrusion, right? Rather than, so this is our tube. And this here represents our mercury, right? So the mercury, those forces are greater. So then you're getting that dome shape, right? Rather than the U shape in the case of water, where water gives us that U shape. This here represents the water down here, right? And that means that those adhesive forces are greater, right? So that's why the sides of the wall is going up higher compared to the center of the molecule. Okay, does that make sense?
Yes, it does.
Okay, well, I know exactly what to put on an exam. Since only one person knows that it makes sense, right? Oops. Oh, and then of course we have wine, right? Everybody spilled wine before?
If we have drank wine before,
Have you spilled wine before? None of you guys
Yeah.
ever spilled wine?
oh,
Yeah.
from my
No.
dad is of course.
Okay, right. So why does it that we're able to sit there and soak up wine in a paper towel? You put a paper towel on it, it soaks up in it. Why?
Because a strong attraction to water.
Because of strong attraction to water, right? Okay, so we know that, is that an adhesive or is that cohesive?
Cohesive? No. Adhesive?
It's adhesive, right? Because opposite, right? You have water and you have the cellulose fibers that are in paper, right? Because wood is basically made up of cellulose. And that's what paper towels are made up of, wood.
At the beginning, I thought because alcohol would attract a little bit.
Oh, alcohol is also going to also attract with cellulose as well too, right? Because it has, if we look at the chemical structure of alcohol, C2H, 5OH, right? So it has that OH there. So it's also going to have dipole forming as well. It's going to have particular hydrogen bonds. Okay.
Mhm.
Yeah, when in doubt, it's always intermolecular forces, right? So you guys are starting to see how it plays a part in it, right? Okay,
Mhm.
so
Yes.
oops. In the case of capillary tube, right? So we can actually calculate how high it's going to go up the capillary tube depending on what we're working with, right? And the way that we would sit there and do that calculation is using this equation here, where we have the height representing the height, it goes up on the capillary tube is equal to 2 times the surface tension. I use ST here. In your book, it uses T. I didn't want to use T because I didn't want you to mistake it for temperature. Times cosine theta. That means the angle that the capillary is held at. And then R represents the radius of the tube. And rho represents density. And G represents gravity. Okay. So if we have water going in a capillary tube, how high will the water rise at 25 degrees? So at 25 degrees, how high will the water rise in the capillary tube with an inner diameter of 0.25 millimeters? For water, the surface tension is 71.99 millinewton per meter. The density is 1 gram per centimeter, and we know that 1 Newton is equal to 1 kilogram per meter second squared. Okay, so what am I going to do?
Wait, can you go back to the equation really quick? I didn't write it down. I'm just gonna take a picture. Okay, I got it. Thank you.
No problem. Okay, there you go. Sorry. Again, my laptop is not behaving today. Okay, so what are we going to do in this case?
Write out the equation or write out the givens.
Okay, so we have 0.25 millimeters. That's going to be our diameter. So diameter. How do I get my radius for my diameter?
Divide by
Divide
2.
by 2.
Okay, so we know that radius is 2r. So we divide this guy by 2. So we'll get 0.125 millimeters. Okay. And that's going to be my radius. Okay. So what is that equation that we have? H equals
2 surface tension cosine over RPG.
R rho G. Okay, so oops, we know that G is going to be 9.8. Meter second squared. So this guy is in millimeters. We should probably put it in meters, wouldn't you guys say? Kind of keep consistent,
Okay.
or no?
Yes.
Okay, so how do I convert this guy into meters?
Divide by 1,000.
Okay, so 1,000 millimeters is equal to 1 meter. Okay, so we have a radius in meters. What about our density? We have density equals 1.0 grams per meters cubed. I mean, per centimeters cubed. And we know that a Newton is going to be kilograms per meters. So should we change the units for these guys?
Yeah.
Okay, so how do I change that into kilograms per cubic meter?
Is kilo 100?
What was that?
Is kilo 100?
Kilo? No, it's not 100. Go up one more. By a factor of 10, 1,000, yeah. So we'll say 1,000 grams equals 1 kilogram. And we have, what about this cubic centimeter? How am I going to get rid of that and get meters?
It would be like 100 cubed.
Okay, so we have 100 cubed.
Yeah.
So
Wait, wouldn't it be on top to cancel out the centimeters?
oh, yep, you're right. So centimeters are canceled out. So this guy would be what, 10 to the 6 So at the end of the day, we have 1,000 kilograms per meter cubed. And then our surface tension, the units for that right now are kilogram. Oops, sorry. That is millinewton per meter. So how many newtons are in a millinewton? Are you there? How many newtons are in a millinewton?
Thousand.
1,000. And we know that 1 Newton is equal to 1 kilogram meters over second squared. Newtons cancel each out, Newton cancel each other out, and we're left with one, two, three. So those meters are going to cancel out. And so we have kilograms over second squared. Is that correct? Or am I just making stuff up? Yes, no, maybe?
Yeah.
Okay.
Maybe.
Yes.
Okay. Then we have the angle. We're going to assume that it's going to be a cosine of 0. Where theta equals 0. And that's going to equal 1. Is that right?
Yes.
Okay. So then we'll have 2 over 2 times 7.199 times 10 to the negative 2. And that's kg over s squared times 1. divided by 1.25 times 10 to the minus 4. And that's meters. Times 1,000 kilograms over cubic meters times 9.8 meters over second squared. Okay, so kilograms cancel out. Second squareds cancel out. This meter leaves me with 1 meter. So then my answer is going to be H equals, what did you guys get? $12, 16, 92, 41. $77. Are you there? What did you guys get?
Honestly, Dr. Henry, I could not find my calculator. I'm looking for it at the moment.
Okay.
I think I know where I left it, but I'm not sure.
Anyone else?
I got a big number. I'm not gonna lie.
You got a big number?
Yeah.
So you should have gotten something like this. So if you look at it, right? This is 10 to the minus 2. So that can cancel out with that. That'll be 10 to the negative 2, but you have 1,000 here, right? So then that's going to make that a small number because that's 10 to the 3 down here, right?
Yes.
Okay. So then we have 10 to the 3 and then 10 to the minus 2. So then that's going to give us a number that is going to be to the, 10 down here, 10 to the 10th. Okay, so if we go 1.2 times 7.199, and we divide that by 9.8 and 1.5 divided by 10, you're going to end up with 0.12 meters. Or 12 centimeters. Simple?
Yes.
Okay. Okay. All right, it's 7 o'clock, right? So I will see you guys on Monday. We'll be finishing up this chapter on Monday, and we'll be finishing chapter 11 on Monday. So bring your A game on Monday.
Got it.
Okay.
Okay.
I will see you guys Monday. Have a good weekend.